In this video, we're going to go over kind of a high-level view of the next two data structures we're going to talk about. So both of these are restricted data structures, which means their functionality is not as open as like an array would be. So they have very particular ways that the data can be accessed. So these restrictions can be helpful when you're using them in a program that requires those particular restrictions. So rather than having to create custom restrictions for every set of data that you have, if you have a problem where the data needs to be accessed in this way by using a stack or a queue, those restrictions are built in, and it makes the job of programming them easier. So the first of these that we're going to talk about is called a stack. So when you think of a stack, I always think of at the cafeteria, there'll be a stack of plates. Often there'll be like an opening in the buffet table, and there'll be a bunch of plates that someone's pushed down. All you can see is the top plate. But when you pull off the top plate, as long as that wasn't the last one, another plate will pop up. Okay. So the idea there is that all you see is that top plate. Okay. So let's look at an example here, and I've got my notes up here until we go to the code. Um, if you have a program, you're in int main, and it calls a function A, let's say it's called, then A calls B, and B calls C. Okay. So the behavior we want is that when C terminates, the execution should go back to B. When B terminates, it goes back to A. Okay, when A terminates, then it goes back to the main, of course. So the computer needs a way to keep track of that as we keep adding function calls. Sometimes our programs can add a lot of those. Okay, there are other cases where we use stacks, but this is just one example. So the way we're going to do this is to use a stack. Okay, so the stack, again, we can only access the top. And when a new item is added to the stack, it it's added to the top, all the others get pushed down. Okay. So that's kind of the basic idea of what we're talking about here. So let's look at some code here. So we start where the program is going to call function A. When it does that, there's an A on the stack. Okay. Function A then calls function B. We now see that B has gone to the top of the stack and that A is pushed down one. Okay. And again, you don't know how many are there. Okay. B calls C. So the function stack has C at the top and then B and then A. Okay. And now let's say that's all and that C terminates. When C terminates, it's taken off the top. So again, it was the last one in, it's the first one out. Okay. And then when B terminates, we're left with only A in our function stack. When A terminates, we're left with an empty stack and we're back in main. Okay. So again, at any point, from a programmatic point of view, we can only see and only deal with what's at the top of the stack. We don't know what's there or what the other stack holds. We don't have any idea. Of course, we could implement a count if we wanted to, but the classic stack doesn't have that. Okay. Uh, so there are some functions that we typically use with stacks. And this varies a little bit from implementation to implementation, but these are the basic ones. So we say that we're going to push a new item onto the stack. Okay, so that will add a new element at the top of the stack. And for this to function correctly, or for this not to have an error, the stack has to exist. Okay, you can't add to a stack that doesn't exist. And the stack can't be full. Okay. The idea of whether a stack can be full or not, we'll talk about in a second. Okay. So we also have, in addition to push, we have top. And what top is going to do, it's going to remove the item from the stack. Sorry, it doesn't do that. In some implications, top will actually return and remove the stack. But I think the way this book does it, is at least is the way it says here, and the way we'll follow, top just returns that item, returns the value of that item. Okay. In other implementations, it may be called peak. You're peaking at the top of the list. Okay. And for this to be true, the stack has to exist, of course, and it can't be empty. Okay. Pop, on the other hand, will remove the element. It doesn't return anything. So we've got the return and the viewing separately. Top lets you see what's on the top of the stack. Pop removes that top item from the stack. And therefore, if there's other items, whatever, there'll be a new top, whichever one the second newest item becomes the new top. Okay. So again, for this, the stack has to exist and it can't be empty. So you can't pop or top off of an empty stack. Okay. We have some other functions that are more helper functions. We have an initialize stack function, which allows us to initialize the stack back to an empty state with no items at all in it. Then we have two Boolean functions, the is empty stack, which will return true if the stack is empty and false otherwise. Okay. Then we have the is full stack, which returns true if the stack is full, false otherwise. Again, those are going to be helpful in dealing with these preconditions for these functions to work. Okay. So this idea of being full or not comes from the options we have when we implement the stacks. So a stack can be implemented either as an array, so just to create a normal array of a set size that would give us that idea for a full or empty. If the array is full, it's full. Okay. Or we could implement it with a linked list in which being full is not quite a problem. Okay. So we can create, again, thinking back to how inheritance works, we're going to capture the behavior of a stack independent of the implementation in this stack abstract data type. Okay. So that will have all of the functionality. It'll have pure virtual functions. We can then implement, okay, so inherit from the stack ADT a version for either arrays or linked list. And that will be in another video. Okay, so let's take a look at what this stack ADT is going to look like. Okay, pop this up. Okay, so let's look at the stack ADT. Okay, so again, this is going to define the behavior. Get this so I can see it. I think you can see it, but it's blocked on my screen. There we go. Okay. Still blocking myself. Fun with Zoom. Okay, so of course this is going to be a templated function, which means we can make it an int, a double, whatever. And again, like with linked list, we'll have to when declaring it, we'll have to put the type in those angle brackets. Okay. So again, the word type here, we always use it, but it's not special. It's just a variable we're choosing to use. Okay. So this is our class stack ADT. We have the following public pure virtual functions. They're pure virtual because they say virtual here, and they have this equals 0, which is weird terminology or weird syntax, but that's how we do it. So we have this initialize stack function. It takes no parameters, and it's a void function. Okay, so that's where we're going to initialize the stack to an empty state. Okay, and when we're done, the stack will be empty. That's the post condition. We have the Boolean functions here is empty stack. Okay. This is a constant function in that it's not going to change the stack any. Okay. So that when again, if the stack is full, or sorry, if the stack's empty, it returns true. If not, it returns false. Okay. The is full stack works the same way, except it checks whether or not the stack is full. Okay. We then have our push function. This is the only one that takes a parameter, and it's going to take this new item. Okay. It's going to be, we've got an ampersand here because we're going to get, this could be a big item. So we're going to send a link basically to that. We're passing it by reference. That's what this means. Okay. That's why we have to put the constant keyword in because we don't want to make a change to the new item. The stack's going to be changed. Okay. If the stack were not going to be changed, we'd have a constant over here. But this constant is going to protect new items from being changed. And again, we will often have stacks of objects of other types. That's why we're going to pass it by reference here. Okay. And then again, it's going to add it to the stack. It'll add it to the top. Okay. It assumes that the stack does exist. And again, it's not full. If it's full, you can't add anything else. Okay. The top then is going to return the top element. Okay. So the push was a void function. The top is of type. Okay. So again, it's a constant function. Top does not change the stack. It just returns what's on top. Okay. Again, it assumes that the stack exists and is not empty. Okay. And then we have pop, which will actually remove that. Again, it's a void function. And all it's going to do is just remove that top element. And then whatever was the second element will become the new top. Okay. And again, it assumes that the stack exists and is not empty. Okay. So one thing that you can do on these, if you type them in, and you'll need to type them in, you can copy them from the book in this case. If you go ahead and do um, a G++ on them, okay, you'll see that it doesn't really return anything. But if there were syntax errors, it would tell you. So if you type something wrong or you have something fouled up, it'll let you know. Okay. So now let's go back and look at queues. So queues are in some ways the opposite of a stack, in that with a queue, it's the first in, first out. Okay, so stacks are last in, first out. Queues are first in, first out. So we don't use it in America much, but the word queue in England refers to just a line. You queue up. Okay, so think of this as a line at a movie theater. So if you go to a movie and you're the first person in line, then you can hope, at least, unless someone's cutting line, that you'll be the first one to be admitted into the movie. Okay. And if you're the 10th person to get there, you'll be the 10th person into the movie. Okay. So with this is a restricted data type as well, but now we're going to um, add new items to either the rear or the back, whichever one you want to call it. That's where we add new items, but we're going to delete items from the front. Okay, so we have a little bit more complexity here. With the stack, everything happens at the top. There's no concept of a bottom. We don't know about it. We don't care about it. But with the queue, we have to know about the front and the back. Okay. So queue has similar operations uh, to the stack, but again, because of this difference, there's a little bit different way to look at it. Okay. So we have the add queue. The add queue in some implementations is called enqueue, ENQUEUE. Okay. But the book's going to call it add queue. We're going to go with that. That allows us to add an item to the rear of the queue. So they're last in line. And again, the queue has to exist, can't be full. Okay. Delete queue, okay, um, is often called DQ, DEQUEUE in other systems, but we're going to call it delete queue. It will remove the item from the front of the list. Okay. So both of these, so again, the queue has to exist. It's not empty. The add queue and the delete queue, neither one return anything. They just make changes to the queue. Okay. We then have the front and the back. Okay, so the front is where we're going to return um, the item that's at the front of the list. Okay, so the queue has to exist and not be empty. Back is going to allow us to return the last element of the queue. Again, it doesn't, neither of these change the queue. It just lets us know what's there. Okay, so we also have the helper functions to initialize the queue to an empty state. We have the is empty and is full. With the is empty returns true if the queue is empty, false otherwise, and the is full returns uh, true if the queue is full and false otherwise. Okay. So again, we're going to take a look at this queue ADT to capture this behavior, but in the same way. So not but, okay. So let's say like stacks, queues also can be implemented either as an array or as a linked list. And if it's implemented as array in particular, then the idea of it being full or empty comes into play. Okay. So let's take a look at this code here. Go back over to the system. Okay, so this again is going to look similar in some ways to the queue. Again, it's a templated function here in that we're going to use this type with a capital T to let us make a queue of ints or doubles or of cars or boats or whatever other custom classes we've created. Okay. So in our per public areas, we have again pure virtual functions with the virtual keyword and the equals 0. Okay. We have a Boolean function is empty queue. Again, it's going to return true if the queue is empty, otherwise it's going to return false. Okay. It's constant here. Both of these first two functions, they're Boolean functions, constants, because we're not going to change the queue just by checking to see if they're empty. And the other one is if it's full. If it's full, it returns true. If not, it returns false. Okay. Again, we initialize the queue. That's a void function that will return it to an empty state. So when we're done with that, the queue is going to be empty. Okay. The front then is going to return something of type. Okay. The queue doesn't change, so it's a constant. So with that one, it's going to have to be where the queue can't be empty, has to exist and not be empty. We'll return that front element. Back works the same way, but it returns the back element, the last one added. Okay. Then we have the add queue or in queue in other systems. And it's going to, just like with the stack, it's going to take a reference to this queue element, which is of type. Okay. And it's constant here. This constant means that this parameter queue element that we're adding to the queue is not changed in the process, but there's no constant over here, so the queue is changed. Okay. So the queue has to exist and the queue has to not be full when we run this. If not, it will if there's no room, it'll create a problem. But if there is room, it'll be added to the back of the list. Okay. And then we have the delete queue, sometimes called DQ, DEQUE, which is going to remove the first element of the queue. Okay. This is how we remove things. Okay. Again, it doesn't return anything. It just removes them. Okay. It removes it from the front of the queue. Okay. So the queue has to exist. The queue has to not be empty. Okay. It can be empty afterwards, but it can't be empty before. Okay. So again, we can run this through G++ to make sure that our syntax is correct. We haven't made any errors. Okay. These are pure virtual functions. All of these functions are pure virtual functions, which means we're not going to create code for any of these functions in the ADT. Sometimes we have some functions that are going to work no matter what, but arrays and linked lists are different enough. There's no real common ground there. Okay. So the next step, which we're going to cover in the next video, is going to be to implement the stack as an array and as a linked list. Those could be separate videos depending on how long they end up being. Okay. We'll then create queues with arrays and queues with linked lists. Okay. So of course, this means that you have to have the linked list.h from the previous chapter and the ordered and unordered list.h, which derive from that. All those have to be functioning or you can't have the queues work. Okay. So I'll say it again that the complexity of our programs is growing pretty quickly. It's important that you build them in pieces and that you compile them frequently to make sure that if there's an error, you know where it's at. Okay. And if you have a problem with your linked list and you try to implement the queue as a linked list, your queue's not going to work, but the problem may not be with the queue. Okay. It may be with the linked list. So you have to make sure that you have a working, tested version of the linked list before you try to use it to build a stack or a queue with. Okay. So this video is just an overview of the data structures we're covering next. So this builds upon the idea of a linked list. And again, like all the data structures we're going to be covering, we're adding in or we're designing in restrictions. In the case of linked lists, sometimes it's more efficient, but also the restrictions are going to help us not have to deal with that. Okay. So I think that's important to keep in mind. I think, again, I think I've said this before, that students will often want to just use an array for everything because you have total access. Okay. But the problem is that's not very efficient and you have to add a whole bunch of code every time. to make it do what you want it to do. Okay. So again, there will be more videos coming soon on how to actually turn these into programs. Okay. But for now, that should be a good start. Again, continue to read the book. Don't just watch the videos. The book has other charts and graphs and illustrations that can be super helpful in understanding this.